Tonight we're going to take a journey into something so ordinary, so woven into the fabric of your daily existence, that you probably never stop to question what it really is. You wake up, you reach for your phone, it's charged. You flick a switch, the room floods with light. You press a button, and a machine hums to life. It all feels so simple, so automatic, so obvious. Electricity is just there, flowing through the walls, waiting to be summoned. But here's the thing that almost nobody realizes. The electricity you use every single day, the force that powers your entire modern existence, is not what you think it is. Not even close. And when you finally understand what it actually is, at the deepest level that human physics has ever reached, you will never look at a light switch the same way again. Let me start with a confession. For most of human history, we had absolutely no idea what electricity was. We used it, or rather, we observed its effects, without understanding its nature. Ancient people saw lightning crack across the sky. They felt static shocks when they touched certain materials and dismissed them as curiosities. They noticed that certain stones attracted iron and built compasses from them, without any clue why they worked. And for thousands of years, that was the extent of human knowledge. We were surrounded by electromagnetic phenomena, living in a world drenched in invisible forces, and we understood none of it. The first glimmer of understanding came from a simple observation, so simple that it's almost embarrassing. Around 600 BC, a Greek philosopher named Thales noticed something odd about amber. Amber is fossilized tree resin, a golden translucent stone that the Greeks prized for making jewelry. And Thales discovered that if you rubbed amber vigorously with fur or cloth, something strange happened. The amber would suddenly attract small, light objects. Bits of straw would leap toward it. Feathers would cling to it. Tiny scraps of dried leaves would stick to it as if pulled by an invisible hand. It was as if the amber had acquired some kind of magical power. Thales had no explanation for this. Nobody did. The Greeks didn't have the conceptual tools to understand invisible forces acting across space. They just noted the phenomenon and moved on. But they did leave us one gift, a word. The Greek word for amber was electron, and from that single word, from that humble observation of rubbed amber pulling on bits of straw, we eventually built an entire vocabulary. Electron, electric, electrical, electronics. All of it traces back to a philosopher playing with a shiny stone 26 centuries ago. For nearly 2,000 years after Thales, almost nothing changed. People knew that certain materials, when rubbed, could attract light objects. They knew lightning existed. They occasionally noticed sparks when combing their hair in dry air, but nobody connected these observations into a coherent picture. Nobody understood what was really happening. The phenomenon remained a parlor trick, an oddity, something interesting but unexplained. Then, in the 1700s, things started to change. Researchers across Europe began experimenting systematically with electrified objects. They discovered that the attractive effect Thales had noticed was not unique to amber. Many materials could be electrified by rubbing. And here's where it got interesting. Glass rubbed with silk behaved differently from amber rubbed with fur. Objects electrified by glass would repel each other, but they would attract objects electrified by amber, and vice versa. This was a critical observation. There weren't just electrified and non-electrified objects. There were two distinct types of electrification, two distinct varieties that interacted with each other in opposite ways. Benjamin Franklin, the American polymath, proposed a brilliantly simple explanation in the 1740s and 1750s. He suggested that what we now call electric charge is a single property that comes in two varieties. Franklin called them positive and negative. He proposed that every object normally has a balanced amount of this property. When you rub two materials together, you transfer some of this property from one to the other. One object ends up with more than its normal share, becoming positively charged. The other ends up with less, becoming negatively charged. Objects with the same type of charge repel each other. Objects with opposite types attract. This simple framework explained every electrical phenomenon Franklin could observe. But more importantly, it introduced something even more fundamental than the idea of two types of charge. It introduced a conservation law. Charge is never created or destroyed. It is only transferred from one object to another. If you rub a glass rod with silk and the glass becomes positively charged, then the silk must become equally negatively charged. The total charge of the system, glass plus silk together, remains exactly what it was before, 0. This conservation of electric charge turns out to be one of the most fundamental laws in all of physics. It has never been violated in any experiment ever conducted. Not once. Every interaction ever observed, from the spark of static on a winter doorknob to nuclear reactions, to particle collisions inside the most powerful accelerators on Earth, conserves electric charge with absolute perfection. But what is charge really? Franklin treated it as a kind of invisible fluid. He imagined positive charge as an excess of electrical fluid and negative charge as a deficit. This fluid model was useful, and it worked well enough for the experiments of his era, but it was not the final answer. Charge as we understand it today is not a substance at all. It is a fundamental property of matter itself. Think of it this way. Matter has several fundamental properties. One of them is mass. Mass tells you how much an object resists acceleration when you push on it, and how strongly it interacts with gravity. You cannot see mass directly. You cannot pour it or bottle it. It is an intrinsic property that matter simply has. Electric charge is similar but different. It is another fundamental property of matter. It is another quality that particles carry. Charge tells you how strongly something interacts with electromagnetic forces. Just as mass determines how an object responds to gravity, charge determines how an object responds to electric and magnetic fields. You cannot see charge any more than you can see mass, but you can observe its effects. In 1785, a French physicist named Charles-Augustin de Coulomb published the precise mathematical law describing how charged objects interact. Using a remarkably sensitive instrument called a torsion balance, he measured the force between charged objects at various distances and with various amounts of charge. What he found was beautifully simple. The force between two charged objects is proportional to the product of their charges and inversely proportional to the square of the distance between them. Double the charge on one object, the force doubles. Double the distance between them, the force drops to 1/4. This is Coulomb's law. And it looks remarkably similar to Newton's law of gravitation, which describes how masses attract each other. Both forces follow the same inverse square pattern. Both act across empty space without physical contact. This deep similarity hints at something profound about the architecture of nature, something we will return to later. Charge also turns out to be quantized. This means it does not come in arbitrary amounts. It comes in discrete, indivisible units. You can have 1 unit of charge, or 2 units, or 17 units, but you cannot have 1.5 units. There is a smallest possible amount of electric charge, and every charged object in the universe carries a charge that is an exact whole number multiple of this fundamental unit. This fact was not obvious to the scientists of Franklin's era. It took more than a century to discover, and the discovery came through one of the most celebrated experiments in the history of physics. But to understand that experiment, we first need to talk about the electron. In 1897, a British physicist named J.J. Thomson was experimenting with cathode rays at the Cavendish Laboratory in Cambridge, England. Cathode rays were mysterious beams produced inside sealed glass tubes when a high voltage was applied between two metal plates. The beams traveled in straight lines, could be deflected by magnets, and made certain materials glow when they struck them. Nobody knew what these beams actually were. Some physicists thought they were waves propagating through a mysterious medium. Others thought they were streams of charged particles. The question was unresolved, and the answer carried enormous implications for our understanding of matter. Thomson designed a series of elegant experiments to settle the debate. He applied both electric and magnetic fields to the cathode rays, and carefully measured how much the beams deflected under each influence. From the amount of deflection, he could calculate the ratio of the particles charged to their mass. The result was astonishing. Whatever these particles were, they had an enormously high charge-to-mass ratio, far higher than any known ion or atom. This meant they were either carrying an enormous amount of charge, or they were incredibly light, or both. Thomson concluded that cathode rays were streams of particles far smaller than any atom, particles that carried negative electric charge. He initially called them corpuscles, but they soon became known by a name derived from that ancient Greek word for amber, electrons. This was revolutionary. For decades, atoms had been considered the smallest units of matter. The word atom itself comes from the Greek atomos, meaning uncuttable. But Thomson had shown that atoms contained even smaller components. Atoms were not indivisible after all. They contained tiny negatively charged particles, electrons, embedded within them. About a dozen years later, the American physicist Robert Millikan performed his famous oil drop experiment. Between 1909 and 1913, Millikan suspended tiny electrically charged oil droplets between parallel metal plates connected to a high voltage source. By carefully adjusting the electric field strength, he could make individual droplets hover in mid-air, perfectly balanced between the downward pull of gravity and the upward push of the electric force. By measuring the voltage needed to suspend each droplet and knowing the droplet's mass from its size and the density of oil, he could calculate the exact amount of charge on each one. What Millikan found was stunning in its simplicity. The charges on the oil droplets were always exact whole number multiples of a single tiny value. One droplet might carry a charge of exactly 1 unit. Another might have exactly 2 units or 5 or 13, but never 1.5 units, never 2.7 units, never anything other than a whole number multiple of that same fundamental quantity. This was direct, irrefutable evidence that electric charge is quantized. There is a fundamental, indivisible unit of charge, the charge carried by a single electron. We now know this value precisely. It is approximately 1.6 times 10 to the negative 19th coulombs. That is an extraordinarily tiny amount of charge. But every bit of electric charge in the entire universe comes in exact multiples of this number. Every charged particle ever detected in every experiment ever performed carries a charge that is a whole number multiple of the electron's charge. Nature simply does not allow fractions. So by the early 1900s, the picture had become much clearer. Matter is made of atoms. Atoms contain electrons, tiny negatively charged particles, surrounding a positively charged nucleus. The electron carries the smallest possible unit of negative charge, and it is these electrons that play the central role in what we experience as electricity in our everyday lives. Not because electrons are electricity itself, but because they are the most common charge carriers in ordinary solid materials. When charge moves through a copper wire, it is electrons doing the moving. When a spark leaps from your finger to a metal doorknob on a dry winter day, it is electrons making that jump. When lightning tears across the sky, it is primarily electrons being driven by enormous electric fields built up inside storm clouds. Electrons are the workhorses of electrical phenomena in the material world. Now here is where things connect directly to electricity as you experience it in daily life. In metals like copper, the material that makes up most electrical wires, atoms are arranged in a regular crystalline lattice. Each copper atom has 29 electrons surrounding its nucleus. Most of these electrons are tightly bound to their parent atoms. They are locked in place, unable to roam. But about 1 electron per atom is loosely bound. It can detach from its parent atom and wander freely through the lattice of the metal. These are called free electrons or conduction electrons. In a piece of copper wire, about the thickness of a pencil, there are roughly 85 billion trillion free electrons in every cubic centimeter of the metal. That is an almost incomprehensible number of mobile charges, all available to participate in electrical activity. And these free electrons are constantly in motion, bouncing around in random directions at high speeds, colliding with the vibrating atoms of the copper lattice, ricocheting off in new directions. then colliding again. Their motion is chaotic, random, and fast. At room temperature, these electrons are zipping around at average speeds of about 1.6 million meters per second. That is fast. About half of 1% of the speed of light. But here is the crucial thing. This motion is entirely random. For every electron moving to the left, there is statistically another electron moving to the right. For every one moving up, another is moving down. The net motion in any particular direction averages out to exactly zero. The electrons are moving incredibly fast, individually, but collectively, they are going nowhere. It is like a crowded room full of people, all walking rapidly in random directions. Enormous activity, but the crowd as a whole is stationary. Now, when you connect a battery or generator to the wire, something changes. An electric field is established along the length of the conductor. This field is subtle, but it gives all those randomly moving electrons a gentle, persistent nudge in one direction. The electrons do not stop their chaotic, random motion. They keep bouncing around at enormous speeds, colliding with lattice atoms millions and millions of times every second. But now, layered on top of all that random movement, there is a tiny, barely perceptible bias, a slight tendency to drift in one particular direction rather than another. This organized drift, this faint directional bias in the otherwise random motion of countless electrons, is what we call electric current. Current is not a substance. It is not a fluid flowing through a pipe. It is a pattern of behavior. It is the organized component of motion among charge carriers. Current is measured in amperes, named after the French physicist André-Marie Ampère. And 1 ampere is defined as 1 coulomb of charge, passing through a given cross-section of wire every second. Since each electron carries about 1.6 times 10 to the negative 19th coulombs of charge, 1 ampere corresponds to roughly 6.25 billion electrons passing a given point every single second. That sounds like an enormous number of electrons, and it is, but remember there are an even more enormous number of free electrons available in even a small piece of copper. The wire does not run out of electrons. The electrons are not consumed or used up. They simply drift through the lattice, nudged along by the electric field, participating in a collective organized motion that we detect and measure as current. And here is where the most shocking revelation arrives. How fast are these electrons actually drifting? You might imagine they are racing through the wire at tremendous speed. After all, when you flip a light switch, the light comes on essentially instantly. The effect seems immediate. Surely the electrons must be moving incredibly fast to deliver that energy so quickly. They are not. The drift velocity of electrons in a typical copper wire carrying a current of about 1 amp is approximately 0.07 millimeters per second. Let me say that again because it is genuinely surprising. The electrons are drifting at roughly 0.07 of a millimeter per second. That is not just slow. That is unimaginably slow. A garden snail, one of the slowest creatures you will ever encounter, moves at roughly 13 millimeters per second. That means the electrons in your household wiring are drifting nearly 200 times slower than a garden snail. 200 times slower than one of the slowest animals on Earth. Think about what this means. If you could somehow tag one particular electron at the point where your wall wire connects to a light switch, and you flip that switch on, that specific electron would take an extraordinarily long time to physically reach the lamp. If the wire from the switch to the lamp was 3 meters long, at a drift velocity of 0.07 millimeters per second, that electron would need roughly 4 hours just to travel 1 meter. To cover the full 3 meters from the switch to the lamp, it would take about 11 or 12 hours. Half a day. You would be waiting from morning to evening for that first electron to physically arrive at the light bulb. But the light turns on instantly. The very moment you flip the switch, the bulb glows. There is no perceptible delay whatsoever. The room goes from dark to bright in a fraction of a second. If it takes an individual electron nearly half a day to drift from the switch to the lamp, how on earth is this possible? Something does not add up. Something else must be happening. Here is an analogy that begins to hint at the answer, though the full picture will take us deeper into physics. Imagine a long tube completely filled with marbles packed end to end with no gaps. Now imagine you push one more marble into one end of the tube. Almost instantly, a marble pops out the other end. The marble that exits is not the same marble you pushed in. That marble is still near the entrance. It barely moved. But the effect of your push, the compression wave, the disturbance, traveled through the entire column of marbles almost instantaneously. Each individual marble only shifted a tiny distance, nudging its neighbor, which nudged its neighbor, which nudged the next, and so on down the line. The individual marbles barely moved, but the signal, the push, the organized disturbance, propagated through the whole system at a speed vastly greater than any single marble's motion. Something similar happens in a wire. When you close a circuit, you do not need to wait for electrons to physically travel from the power source to the device. The wire is already full of free electrons everywhere along its entire length. When an electric field is established, it does not push electrons from one end all the way to the other like water being forced through a hose. It nudges all the electrons along the wire simultaneously, everywhere at once, causing them all to begin their slow drift at approximately the same moment. The effect, the signal, the establishment of current propagates at close to the speed of light, even though the electrons themselves are barely crawling. But here is where the marble analogy breaks down, and where the real physics becomes far more interesting and far more counterintuitive. In the marble tube, the energy transfers from marble to marble through physical contact. The marbles are both the carriers of the signal and the carriers of the energy. Kinetic energy flows through the chain of marbles as each one pushes the next. In an electrical circuit, this is not what happens. The electrons are not carrying the energy through the wire the way marbles transfer a push through a tube. The energy in a circuit does not travel through the wire at all. This is one of the most surprising and counterintuitive facts in all of physics, and it catches virtually everyone off guard the first time they hear it. The wire is essential. Without it, nothing works. But the wire's role is not to act as a pipeline through which energy flows like water through plumbing. The wire acts more like a guide, a track, a set of railroad rails that determine where something else travels. The energy itself moves somewhere else entirely. It travels through the space around the wire, carried by something called the electromagnetic field. This is not a minor technical detail. It is not a footnote in a physics textbook. It fundamentally changes what electricity is. Electricity is not electrons flowing through a wire like water through a pipe. The electrons barely move. The energy does not travel inside the conductor at all. The real story of electricity is the story of the electromagnetic field, an invisible physical entity that fills the space around and between charges, carrying energy and transmitting forces at enormous speed. And that field, the electromagnetic field, is one of the most important discoveries in the entire history of human knowledge. If you want to understand what electricity is truly made of, you cannot just look at the electrons. You have to understand the field, because the field is where the energy lives. The field is what actually delivers power from a generating station to your home. The field is what makes the light turn on the instant you flip the switch, even though the electrons in the wire are drifting nearly 200 times slower than a snail. And the story of how that field was discovered, what it is, and how it works, is one of the most extraordinary chapters in all of science. The discoveries that charge comes in two types: that charge is always conserved, that it is quantized in units of the electron's charge, and that current is the organized drift of charge carriers. These are crucial foundations. Without them, nothing else makes sense. But they are only the beginning of the story. They tell us what the ingredients are, but not how the recipe works. They tell us about the players on the field, but not about the game itself. The game, the real mechanism behind everything we call electricity, lies in the electromagnetic field. And to appreciate what the electromagnetic field truly is, we need to understand something that was far from obvious to the scientists who first encountered electrical phenomena. For centuries, people assumed that forces between objects required direct physical contact. You push a cart, it moves. You throw a ball, it flies. Everyday experience involves objects interacting by touching each other. But electric charge introduced something deeply unsettling. Two charged objects separated by empty space with nothing visible between them exert forces on each other. They attract or repel without any physical contact whatsoever. How? What is reaching across that gap? What invisible mechanism is transmitting force through empty space? This question haunted physicists for generations. Newton had grappled with exactly the same problem when it came to gravity. Two massive objects attract each other across empty space. Newton described the mathematics of this attraction perfectly with his law of universal gravitation, but he was profoundly uncomfortable with the idea of action at a distance. He wrote that one body acting upon another through a vacuum without any intermediary was so great an absurdity that no competent thinker could accept it. Yet he could not explain how gravity reached across empty space. He simply accepted that it worked and moved on. Electric forces presented the same deep puzzle, but with an additional twist. Unlike gravity, which is always attractive, electric forces can be either attractive or repulsive depending on the signs of the charges involved. And unlike gravity, which is extraordinarily weak at the level of individual particles, electric forces are enormously powerful. The electromagnetic force between two electrons is roughly a 1, followed by 42 zeros times stronger than the gravitational force between those same two electrons. That is an almost meaningless number in its enormity. Electromagnetism utterly dominates gravity at the scale of atoms and molecules. The fact that gravity seems strong to us in everyday life, that we feel its pull so powerfully, is only because the Earth is enormously massive, and because most of its electric charges cancel out, positive balancing negative almost perfectly. The gravitational pull of an entire planet is needed just to compete with the electromagnetic forces holding together the atoms in your shoes and the floor beneath your feet. So, how do charged objects influence each other across empty space? What reaches across that gap? The answer, developed over the course of the 1800s through the work of brilliant experimentalists and theorists, would completely transform physics. It would unify electricity, magnetism, and light into a single breathtaking framework. It would reshape our understanding of energy, space, and the fundamental nature of reality. And it all begins with the concept of the field, an invisible but very real physical entity that fills the space around every charged particle, reaching out in all directions, ready to push or pull on any other charge that wanders into it. The electromagnetic field is not a mathematical abstraction. It is not just a convenient bookkeeping trick that makes calculations easier. The electromagnetic field is a real physical thing. It carries energy. It carries momentum. It exerts forces. It exists in the space around you right now, generated by every charged particle in your body, in the walls around you, in the ground beneath your feet. It is everywhere. And it is the key to understanding what electricity actually is. Because electricity, at its deepest level, is not about electrons alone. It is about the interplay between charged particles and the electromagnetic field that connects them. The electrons provide the charge. The field provides the interaction. Together, they create everything we experience as electricity. From the spark of static on a dry winter day, to the power grid that lights up entire continents at the flick of a switch. And the deeper we look into the nature of that field, the more extraordinary and the more quantum the picture becomes. At the close of the 1700s, scientists had a solid understanding of electric charge. They knew charge came in two types, positive and negative. They knew like charges repel and opposite charges attract. They had Coulomb's law, a precise mathematical description of the force between charges. But there was a gaping hole in their understanding. Nobody could explain how charged objects exerted forces on each other across empty space. Something invisible reached between them, transmitting attraction or repulsion through what appeared to be nothing at all, and nobody knew what that something was. Meanwhile, an entirely separate branch of science had been developing for centuries: magnetism. Humans had known about magnets since antiquity. Lodestones, naturally magnetized pieces of iron ore, could attract iron and align themselves roughly north and south. The compass, one of the most transformative inventions in human history, was based on this property. By the 1700s, the science of magnetism was well established. Magnets have north and south poles. Opposite poles attract, like poles repel. And magnets, like electric charges, exert forces across empty space without physical contact. For a long time, electricity and magnetism were considered completely separate phenomena. They seemed to have nothing to do with each other. Electric forces came from charges. Magnetic forces came from magnets. The two fields of study existed side by side, but did not overlap. And then, in the spring of 1820, everything changed. A Danish physicist named Hans Christian Ørsted was giving a lecture demonstration in Copenhagen. He had a compass sitting on a table near a wire connected to a battery. When he closed the circuit and current flowed through the wire, the compass needle deflected. It swung away from magnetic north and pointed instead, roughly perpendicular to the wire. When Ørsted turned off the current, the needle swung back to north. He tried it again. Same result. Current on. The needle moves. Current off. It returns to normal. This was extraordinary. An electric current was producing a magnetic effect. Electricity and magnetism, those two supposedly separate phenomena, were connected. They were not independent forces at all. They were somehow related. One could produce the other. This discovery, simple as it seems in hindsight, sent shockwaves through the scientific world. Within weeks, physicists across Europe were replicating and extending Ørsted's experiment. André-Marie Ampère in France quickly developed mathematical laws describing how currents produce magnetic forces. The race was on to understand the deep connection between electricity and magnetism, and this is where one of the most remarkable figures in the entire history of science enters the story: Michael Faraday. Born in 1791 in South London to a poor family, Faraday left school at 13 and was apprenticed to a bookbinder. But he was consumed by curiosity. He read every science book that came through the shop, attended public lectures whenever he could, and taught himself chemistry and physics from the ground up. Through a combination of talent, persistence, and extraordinary luck, Faraday eventually secured a position at the Royal Institution in London, one of the premier scientific establishments in the world. And there, over the course of several decades, he conducted experiments that would reshape the foundations of physics. Faraday was not a mathematician. He could not write equations. He thought in pictures, in physical intuitions, in vivid mental images of invisible processes. And this apparent weakness turned out to be one of the greatest strengths in the history of science. Because Faraday's visual, intuitive way of thinking led him to see something that the mathematically trained physicists of his era completely missed. After Ørsted showed that electric currents produce magnetic effects, the obvious question was whether the reverse was also true. Could magnetism produce electricity? Many scientists tried and failed. Faraday spent years pursuing the question, and in 1831 he cracked it. He discovered electromagnetic induction, the principle that a changing magnetic field produces an electric current, not a static magnetic field, a changing one. If you hold a magnet still near a coil of wire, nothing happens. No current flows. But if you move the magnet, if you change the magnetic field passing through the coil, current appears in the wire. Push the magnet in, current flows one way. Pull the magnet out, current flows the other way. Stop the motion, and the current vanishes. This discovery was monumental for practical reasons. It is the principle behind every electrical generator on Earth. Every power plant, whether it burns coal, splits atoms, captures wind, or harnesses falling water, produces electricity by the same fundamental mechanism. Something spins a turbine, which rotates magnets near coils of wire, which creates a changing magnetic field, which induces electric current. Faraday's 1831 discovery powers modern civilization. Virtually every watt of electrical energy consumed on this planet traces its origin back to electromagnetic induction. But Faraday's contribution went far beyond the practical. His deepest contribution was conceptual. While thinking about how electricity and magnetism interact across empty space, Faraday developed an idea that was radically different from anything his contemporaries had proposed. He imagined that every magnet and every charged object was surrounded by invisible lines of force, radiating outward into space. These lines were not just convenient drawings. Faraday believed they were real physical entities. They filled the space around every charge and every magnet, stretching out in all directions, creating a web of invisible influence. When another charge or magnet entered this web, it felt a force because it was interacting with these lines of force. The force was not transmitted instantaneously across empty space by some mysterious action at a distance. It was transmitted locally from one tiny region to the next through these invisible lines filling the space between the objects. The charged objects did not reach out and grab each other across the void. Instead, each charge influenced the space immediately around it. That influence spread outward through the lines of force, and when the lines reached another charge, that charge responded. This was the birth of the field concept. Faraday had invented what we now call the electromagnetic field, not a mathematical abstraction, but a real physical thing, occupying real space, carrying real energy, transmitting real forces. Most of the leading physicists of Faraday's era dismissed his lines of force as a quaint visualization, unsuitable for serious mathematical physics. They preferred the clean precision of action at a distance equations like Coulomb's law, which gave exact answers without needing to worry about invisible lines filling space. Faraday, who could not express his ideas in mathematical language, struggled to convince his peers that his vision was more than just a pretty picture. It took a young Scottish physicist named James Clerk Maxwell to prove that Faraday was right, and to transform Faraday's visual intuition into one of the greatest mathematical achievements in human history. Maxwell was Faraday's opposite in many ways. Where Faraday was self-taught and intuitive, Maxwell was formally educated and mathematical. Where Faraday thought in pictures, Maxwell thought in equations. But Maxwell recognized the genius in Faraday's lines of force. He saw that Faraday had grasped something deep about the nature of reality, something that the mathematically sophisticated but conceptually limited action at a distance theories had missed entirely. And Maxwell set out to translate Faraday's physical intuitions into rigorous mathematical language. What Maxwell produced over the course of the 1850s and 1860s was breathtaking. He developed a set of equations describing the behavior of electric and magnetic fields. These equations, eventually distilled into the compact form we know today, captured the entire behavior of electricity and magnetism in 4 elegant mathematical statements. They described how electric charges create electric fields, how moving charges create magnetic fields, how changing magnetic fields create electric fields, which was Faraday's discovery of induction, and how changing electric fields create magnetic fields, which was Maxwell's own profound addition. That last point deserves special emphasis because it was entirely Maxwell's contribution, a theoretical prediction with no experimental basis at the time. Maxwell realized that if a changing magnetic field creates an electric field, as Faraday had shown, then by the deep symmetry of the equations. A changing electric field should also create a magnetic field. This was not something anyone had observed. It was a prediction arising purely from the mathematical structure of the theory, and it had staggering consequences. Because when Maxwell worked through the mathematics, when he combined his 4 equations and solved them for what happens when electric and magnetic fields interact and reinforce each other, something miraculous emerged. The equations predicted that electric and magnetic fields could sustain each other in a self-propagating wave. A changing electric field creates a magnetic field. That changing magnetic field creates an electric field. That electric field creates more magnetic field. The 2 fields leapfrog through space, each one generating the other, advancing together as a wave that requires no medium, no wire, no material substance to carry it. And when Maxwell calculated the speed at which this wave would travel, the speed fell directly and unambiguously out of the fundamental constants of electricity and magnetism. 2 numbers that had been measured independently in laboratories, one describing the strength of electric forces and the other describing the strength of magnetic forces, combined to predict a wave speed of approximately 300,000 kilometers per second. This number was already known. It was the speed of light. Maxwell had not set out to explain light. He was studying electricity and magnetism. But his equations told him, with unavoidable mathematical certainty, that electromagnetic waves travel at exactly the speed of light. This could not be a coincidence. Maxwell drew the only possible conclusion. Light is an electromagnetic wave. Light is not a separate phenomenon. It is electricity and magnetism propagating together through space as a self-sustaining wave of oscillating fields. This unification of light, electricity, and magnetism into a single framework is one of the most staggering achievements in the history of human thought. 3 phenomena that had seemed completely unrelated, the spark from a rubbed piece of amber, the pull of a lodestone, the light that fills a room when you open the curtains, turned out to be 3 aspects of the same underlying thing. The electromagnetic field, everything from radio waves to microwaves to infrared to visible light to ultraviolet to gamma rays, is an electromagnetic wave. They differ only in wavelength and frequency, but they are all the same fundamental phenomenon, oscillating electric and magnetic fields propagating through space at the speed of light. And the speed of light itself is not a property of light specifically. It is a property of the electromagnetic field built into the structure of the equations that govern all electromagnetic phenomena. In 1887, about 2 decades after Maxwell published his theory, a German physicist named Heinrich Hertz experimentally confirmed the existence of electromagnetic waves. Using a spark gap transmitter and a simple loop antenna, Hertz generated and detected radio waves in his laboratory. He showed they could be reflected, refracted, and polarized just like light. They traveled at the speed of light, exactly as Maxwell had predicted. Hertz had produced light, in a sense, from an electric circuit, not visible light, but electromagnetic radiation of a longer wavelength. The unification was complete. Now, why does all of this matter for understanding what electricity is? Because the electromagnetic field is not just an interesting theoretical concept, it is where the energy lives. It is what actually carries power through an electrical circuit. And this is where the story takes its most counterintuitive turn. When you flip a switch and electricity flows through a circuit, where is the energy? Most people assume it is inside the wire, carried by the electrons. After all, the wire is the physical thing you can see and touch. The electrons are real particles inside the wire. The energy must be traveling through the wire, carried by those moving electrons. Right? Wrong. The energy in a circuit is not inside the wire. The energy is in the electromagnetic field surrounding the wire. It travels through the space outside the conductor, guided by the wire, but not contained within it. The wire is essential, but its role is not to act as a pipe carrying an energy fluid. Its role is to act as a guide, shaping the pattern of the electromagnetic field in the space around it, determining where the energy flows and where it goes. The wire is like railroad tracks. The train, the energy, runs along the tracks, but the train is not inside the metal of the rails. The train runs on top of them, guided by them, directed by them. Remove the tracks, and the train cannot follow its route. But the tracks themselves are not carrying the train inside their metal structure. This is not a metaphor or an approximation. It is a precise, measurable, physical reality. In 1884, a British physicist named John Henry Poynting published a paper showing exactly how to calculate the flow of electromagnetic energy through space. The mathematical quantity he defined, now called the Poynting vector, describes the direction and rate of energy flow at every point in space around a circuit. And when you apply the Poynting vector to a simple circuit, a battery connected to a light bulb by copper wires, the result is startling. The energy flows outward from the battery into the space surrounding the wires. It then propagates through the space outside the wires, guided along by the electromagnetic field pattern that the wires and the current inside them establish. The energy converges inward toward the light bulb, where the electromagnetic field surrenders its energy to the resistance in the filament, heating it until it glows. At every point along the circuit, the energy is traveling through the space around the wire, not through the metal of the wire itself. Some of the energy does enter the wire. A small fraction of the total energy flow is directed inward from the surrounding field into the conductor. This inward flowing energy is what heats the wire, what produces resistance losses, what makes a wire feel warm when current flows through it. The energy dissipated as heat inside the wire was never carried along the wire from the power source. It entered the wire from the outside, from the surrounding electromagnetic field, absorbed by the conductor as the field penetrated slightly into the metal. Even the heating of a wire is caused by energy flowing from the field into the wire, not by energy traveling along the wire from one end to the other. This completely inverts the common picture. The wire does not deliver energy the way a pipe delivers water. The field delivers the energy. The wire merely shapes the field. Without the wire, the field would not have the correct geometry to funnel energy from the source to the load. But without the field, the wire is just a piece of inert metal sitting there doing nothing. And this explains, at last, the mystery of the light that turns on instantly, even though the electrons drift slower than a snail. When you flip a switch, you are not pushing electrons from the switch to the lamp. You are establishing an electromagnetic field throughout the entire circuit. That field propagates at close to the speed of light. In a typical household wire, the signal propagation speed is somewhere between 50 and 99% of the speed of light, depending on the materials surrounding the wire. For a wire 3 meters long, the electromagnetic signal reaches the lamp in roughly 10 to 20 nanoseconds. That is 10 to 20 billionths of a second, essentially instantaneous by any human perception. The field arrives almost instantly. It establishes itself around the entire circuit in a fraction of a microsecond. And once the field is established, it begins funneling energy from the source through the surrounding space to the lamp. The electrons have not moved any appreciable distance in this time. They have barely begun their glacially slow drift. But the energy has already arrived, carried by the field at nearly the speed of light. Think about what this means for the wires running through your walls right now. If there is current flowing, if a lamp is on, or an appliance is running, the energy powering those devices is not traveling inside the copper. It is traveling through the space inside your walls, through the air, through the insulation, through the plaster and paint, flowing in the electromagnetic field that surrounds the wires. The wires guide this energy flow, shaping it, directing it. But the energy itself is in the field, not in the metal. This also clarifies something important about what a battery or generator actually does. A battery does not store electricity. It stores chemical energy. When you connect a battery to a circuit, the chemical reactions inside the battery maintain a difference in electric potential between its two terminals. This potential difference creates an electric field in the space around the wires. The electric field, combined with the magnetic field produced by the resulting current, creates the electromagnetic field pattern that carries energy from the battery to whatever device is connected to it. The battery is an energy source that creates and maintains the conditions for the electromagnetic field to do its work, but the delivery mechanism is the field itself. A generator works similarly, but instead of using chemical reactions, it uses Faraday's electromagnetic induction. Rotating magnets create changing magnetic fields, which create electric fields, which drive current, which creates a self-consistent electromagnetic field pattern that transmits energy from the generator through the fields surrounding the wires to homes and businesses. The power grid that lights up cities and runs factories is, at its core, a vast network of guided electromagnetic fields. The wires and cables stretching across the landscape are not pipelines carrying a fluid called electricity. They are guides, shaping an enormous electromagnetic field structure that carries energy through the space around the conductors. This field carries energy from generating stations to homes, from power plants to hospitals, from solar panels to air conditioners, and it does it at nearly the speed of light, even though the electrons in the wires barely drift at all. Let me push this further so the picture becomes truly sharp. Imagine you could somehow make the electromagnetic field visible. You would see energy radiating outward from every battery terminal and every generator output. You would see it streaming through the space around every wire in your house, flowing along the walls, guided by the copper conductors hidden inside. You would see it converging inward toward every light bulb, every toaster, every phone charger, pouring into the device from the surrounding field. The wires would appear as dark channels, guiding a river of invisible energy that flows not through them, but around them. The space itself would be alive with energy in transit. This picture is not science fiction. It is the actual, literal, measurable physics of how electricity works. And it has been understood by physicists since the 1880s, since Poynting and his contemporary Oliver Heaviside independently worked out the mathematics of electromagnetic energy flow. Heaviside, a brilliant and eccentric self-taught physicist, reformulated Maxwell's equations into the compact vector form we use today, and was among the first to clearly articulate that electromagnetic energy flows through the field, not through the wire. He was decades ahead of his time in understanding the implications. Yet this understanding has never fully penetrated public awareness. The water in a pipe analogy is so intuitive and so easy to teach that it persists in textbooks and popular science to this day. For practical purposes, if you are an electrician wiring a house, the fluid analogy works well enough. But if you want to understand what electricity actually is, the fluid analogy is actively misleading. It places the energy in the wrong location and hides the deep physics that truly governs how electromagnetic energy moves from place to place. So where are we now in our understanding? We know that electric charge is a fundamental property of matter. We know that electrons are the most common charge carriers in ordinary solid materials. We know that electric current is the organized drift of charge carriers, and that this drift is extraordinarily slow. We know that the electromagnetic field is a real physical entity, filling the space around every charge and every current, carrying energy and transmitting forces. We know that energy in an electrical circuit travels through the field surrounding the wires, not through the metal of the wires themselves. We know that the signal establishing this field propagates at close to the speed of light, which is why the light turns on instantly, even though the electrons themselves are barely moving. This picture is already far richer and more accurate than the flowing fluid model most people carry in their heads, but it is still not the complete picture. Because everything described so far, Faraday's field, Maxwell's equations, the Poynting vector, all of this is classical physics. It is physics that treats the electromagnetic field as a smooth, continuous entity and treats electrons as tiny particles following definite paths. And while this classical picture works beautifully for circuits and generators and power grids, it is not the final word. When you zoom in to the scale of individual atoms, when you look at what electrons actually do inside a solid material, the classical picture breaks down. Electrons inside a crystal lattice do not behave like tiny billiard balls rolling through corridors. They behave as quantum particles governed by the strange and counterintuitive rules of quantum mechanics. Their behavior inside matter, the way they organize themselves, the way they respond to fields, the reason some materials conduct electricity and others do not, all of this requires quantum mechanics to explain. And that quantum story, the story of what electrons actually do inside solid matter, reveals an entirely new layer of depth to the question of what electricity is. Because the answer to why copper conducts electricity, while glass does not, the answer to why some materials resist current while others carry it effortlessly, the answer to why certain exotic materials can carry current with absolutely zero resistance at all of these answers lie in quantum mechanics. And they are some of the most beautiful and surprising results in all of physics. So far, we have discovered that electricity is not a flowing substance. We have learned that the electrons in a wire drift at a pace slower than a snail, and that the energy powering your devices travels through the electromagnetic field surrounding the wire, not through the metal itself. This picture is already far more accurate than anything most people learn in school, but it leaves a fundamental question unanswered. Why does copper carry electricity so well, while rubber does not? Why does glass block the flow of charge almost completely, while aluminum lets it pass with barely any resistance? If electricity is really about charges responding to electromagnetic fields, why do some materials let their charges respond freely, while others lock them rigidly in place? The answer lies inside the material itself, at the scale of individual atoms, where the rules of physics change completely. Because at the atomic scale, the classical picture of electrons as tiny particles bouncing around like billiard balls simply does not work. Down here, electrons obey quantum mechanics, and quantum mechanics paints a picture of the interior of a solid that is unlike anything you would intuit from everyday experience. To understand this quantum picture, we need to begin with what quantum mechanics tells us about a single atom. In the classical picture that emerged in the early 1900s, an atom looks like a miniature solar system. A dense, positively charged nucleus sits at the center, and electrons orbit it like tiny planets, circling in definite paths at definite speeds. This image is vivid, intuitive, and almost entirely wrong. Quantum mechanics, developed through the 1920s by physicists including Erwin Schrödinger, Werner Heisenberg, and others, revealed that electrons in atoms do not follow definite orbits. They do not trace neat circular paths. Instead, each electron exists as a wave function, a mathematical object that describes the probability of finding the electron at any given location. The electron does not have a precise position until you measure it. Before measurement, it exists in a spread-out cloud of probability, a quantum haze that fills a region of space around the nucleus. These probability clouds have specific shapes. Some are spherical, others are dumbbell-shaped, others have more complex lobed structures. But the crucial point is that each cloud corresponds to a specific energy. An electron in one orbital has a definite energy. An electron in another orbital has a different energy. The electron cannot have just any energy it pleases. It can only occupy certain, specific, quantized energy levels. The energies are discrete, like the rungs of a ladder. You can stand on the first rung or the second rung, but you cannot stand between rungs. There is no in-between. The electron can be in one allowed state or another, but it cannot exist in a state with an energy that falls between the allowed values. This quantization of energy is one of the most fundamental features of quantum mechanics. It is why atoms absorb and emit light only at specific wavelengths, When an electron jumps from a higher energy level to a lower one, it emits a photon whose energy equals the difference between the two levels. When an electron absorbs a photon with exactly the right energy, it jumps up to a higher level. Only photons with energies matching the gaps between levels are absorbed or emitted. This is why neon signs glow red. It is why sodium lamps glow yellow. It is why every element produces a unique fingerprint of spectral lines. The specific pattern of allowed energy levels is different for every type of atom, and the colors of light emitted correspond to the specific gaps between those levels. Now, here is where things become truly interesting for understanding electricity. A single isolated atom has a set of discrete energy levels, sharply defined with clear gaps between them. But in a solid material, atoms are not isolated. They are packed closely together, billions upon billions of them, arranged in a regular repeating structure called a crystal lattice. In a typical metal like copper, each atom sits roughly 0.2 of a nanometer from its neighbors. At this distance, the electron clouds of neighboring atoms overlap. The outer electrons of each atom interact not just with their own nucleus, but with the nuclei and electrons of surrounding atoms. This interaction has a profound effect on the energy levels. When two identical atoms are brought close together, their identical energy levels split into two slightly different levels. Bring 3 atoms together and the level splits into 3. 1,000,000 atoms give 1,000,000 levels, so closely spaced they are practically indistinguishable. In a real solid, there are not 1,000,000 atoms. There are roughly 100 billion trillion atoms in a single cubic centimeter of material. Each original atomic energy level splits into roughly 100 billion trillion extremely closely spaced levels. These levels are so densely packed that they form a continuous band of allowed energies. What was once a single sharp energy level in an isolated atom becomes a broad band of allowed states in a solid. And what was once a gap between two levels in an isolated atom becomes a gap between two bands in a solid. This gap is called a band gap, and it is one of the most important concepts in all of solid-state physics. The band structure of a solid determines almost everything about its electrical behavior. This is the quantum mechanical answer to the question of why some materials conduct electricity and others do not. It all comes down to which bands are filled, which bands are empty, and how large the gaps between them are. To understand this, we need one more principle from quantum mechanics, and it is arguably one of the most important principles in the entire framework. It is called the Pauli exclusion principle, named after the Austrian physicist Wolfgang Pauli, who formulated it in 1925. The principle states that no two electrons in a system can occupy exactly the same quantum state simultaneously. Every electron must differ from every other electron in at least one quantum property. Two electrons can share the same energy level, but only if they have opposite spin, a quantum mechanical property that comes in two varieties, commonly called spin up and spin down. Once both spin states are filled at a given energy level, that level is full. No more electrons can enter it. Any additional electrons must go to a higher energy level. This principle has enormous consequences for solids. Imagine filling the energy bands of a solid with electrons, starting from the lowest energy states and working upward. Each state holds at most 2 electrons, one spin up and one spin down. You keep filling from the bottom. At some point, you run out of electrons. The last band that contains electrons might be completely full, or it might be only partially full. And this distinction makes all the difference in the world. In a metal like copper or aluminum, the highest occupied energy band is only partially filled. There are plenty of electrons in this band, but there are also plenty of empty states available at energies just barely above the occupied states. The filled states and the empty states exist within the same band with no energy gap between them. When you apply an electric field to the metal, electrons in the partially filled band can easily shift into the nearby empty states. They can gain a tiny amount of energy from the field and move into a slightly higher state within the same band. This change in states corresponds to a net drift of electrons through the material. The electrons respond to the field by rearranging themselves among the available states, and this rearrangement constitutes electric current. This is why metals conduct electricity. Not because their electrons are somehow free to fly around unimpeded, but because the quantum mechanical band structure provides empty states immediately adjacent in energy to the filled states. The electrons can respond to even a tiny electric field because there is always room for them to shift into slightly higher energy states. There is no energy barrier to overcome. The door is always open. Now consider an insulator like diamond or glass. In these materials, the highest fully occupied band, called the valence band, is completely full. Every single state in that band is occupied. There is no room for any electron to shift to a nearby state, because every nearby state is already taken. And the next available band of states, called the conduction band, is separated from the valence band by a large energy gap. In diamond, this gap is about 5.5 electron volts. That might not sound like much in everyday terms, but at the atomic scale, it is enormous. The energy provided by an ordinary electric field, the kind you get from a household battery or wall outlet, is nowhere near enough to push an electron across this gap. The electrons are stuck. They cannot respond to the applied field because there is literally nowhere for them to go. Every state in their band is occupied, and the next available states are separated by an energy chasm they cannot cross. This is why insulators do not conduct electricity. The electrons are not physically locked in place by chains or barriers. They are quantum mechanically locked in place by the Pauli exclusion principle and the band gap. Every state they could shift into within their own band is already full, and the states in the next band are too far away in energy to reach. The electrons have no available pathway to respond to an electric field, so they sit still and no current flows. Between these two extremes lie semiconductors. Materials like silicon and germanium have a band structure similar to insulators with a completely full valence band and an empty conduction band. But the band gap is much smaller. In silicon, the gap is about 1.1 electron volts. In germanium, it is about 0.67 electron volts. These gaps are small enough that under certain conditions, some electrons can be promoted across the gap into the conduction band, where they are free to move and carry current. At extremely low temperatures near absolute zero, a pure semiconductor behaves like an insulator. The thermal energy available is not enough to push electrons across the gap. But as the temperature rises, more thermal energy becomes available. Atoms in the crystal lattice vibrate more vigorously, and occasionally the thermal jostling gives an electron enough energy to jump across the band gap into the conduction band. Once in the conduction band, that electron can move freely and carry current, just like electrons in a metal's partially filled band. And the hole it left behind, in the valence band, the empty state, also contributes to conduction. Other electrons in the valence band can shift into that hole, effectively moving the hole through the material like a bubble rising through water. The hole behaves as though it is a positively charged particle moving through the lattice. This is one of the most elegant and counterintuitive results in solid-state physics. When an electron jumps up to the conduction band, it leaves behind a hole in the valence band, and both the electron and the hole can carry current. The semiconductor has two types of mobile charge carriers, negative electrons in the conduction band and positive holes in the valence band. This temperature sensitivity is why semiconductors are so useful for electronics. Their conductivity can be precisely controlled by adding tiny amounts of impurity atoms to a semiconductor crystal, a process called doping. Engineers can dramatically change the material's electrical behavior. If you add atoms with one extra electron compared to the host material, those extra electrons sit at energy levels just below the conduction band. They can easily jump into the conduction band with very little thermal energy, greatly increasing the number of mobile electrons. This creates a material rich in negative charge carriers, called an N-type semiconductor. If you add atoms with one fewer electron, they create empty states just above the valence band. Electrons from the valence band can easily jump into these states, creating holes that carry positive charge. This creates a p-type semiconductor. By combining n-type and p-type regions in clever configurations, engineers build transistors, diodes, solar cells, and every other component that makes modern electronics possible. Every smartphone, every computer, every digital device on Earth relies on the quantum mechanical band structure of semiconductors. The entire digital revolution is built upon the gap between the valence band and the conduction band in silicon crystals. Now let us turn to what happens when electrons do conduct when they are moving through a material in response to an electric field. In a perfect crystal, in a lattice where every atom sits exactly in its ideal position and nothing disturbs the regular pattern, an electron moving through the conduction band would actually encounter no resistance at all. This sounds surprising, but it is a direct consequence of quantum mechanics. Felix Bloch showed in the late 1920s that an electron wave propagating through a perfectly periodic crystal lattice travels without any scattering. The electron's wave function extends coherently across the entire crystal, fitting perfectly into the repeating pattern of the lattice. This result, known as Bloch's theorem, tells us something remarkable. Electrical resistance is not intrinsic to the conduction process itself. If the lattice were perfect, current would flow forever without any resistance once started. Think about this with an analogy. Imagine a perfectly smooth, infinitely long highway with no potholes, no debris, no curves, no friction, nothing to slow you down. Once your car reaches cruising speed, it would coast forever without needing any fuel. The road itself offers no resistance. Now imagine a real highway. It has cracks, bumps, rough patches, construction zones, gravel, expansion joints. Every imperfection jolts your car, sapping energy, slowing you down. You need to keep your foot on the gas just to maintain speed because the road constantly steals energy from you through these imperfections. A perfect crystal lattice is like the first highway. An electron wave moves through it without losing energy. A real crystal is like the second highway. Imperfections constantly scatter the electron, draining its organized motion and converting it into heat. Resistance arises because real crystals are not perfect. Real crystals have imperfections. There are several sources of imperfection that scatter electrons and create resistance. The most important, under normal conditions, is thermal vibration. At any temperature above absolute zero, the atoms in the lattice vibrate around their equilibrium positions. These vibrations are quantized, meaning they come in discrete packets of energy called phonons. Think of phonons as quanta of sound, just as photons are quanta of light. Phonons represent the quantized vibrations of the crystal lattice. When a conduction electron encounters a phonon, it can scatter, changing direction and losing or gaining energy. This scattering disrupts the electron's orderly drift through the material. It is like trying to walk in a straight line through a crowded room where people keep bumping into you. Each collision deflects you from your path. You still make forward progress on average, but much more slowly than you would in an empty room. This phonon scattering is the dominant source of electrical resistance in metals at room temperature. It is why resistance increases with temperature. Higher temperature means more vigorous lattice vibrations, more phonons, more scattering events, and therefore more resistance. Crystal defects also scatter electrons. Real crystals always have imperfections, missing atoms, foreign atoms replacing normal ones, displaced rows. These defects break the perfect periodicity of the lattice. Impurity atoms present a different potential to the passing electron than the regular lattice atoms, and electrons scatter off them. A copper wire always contains trace amounts of other elements, and each foreign atom is a scattering center that contributes to resistance. This is why the purity of a conductor matters. Extremely pure copper has lower resistance than copper with significant impurity content. Crystal boundaries also scatter electrons. In a polycrystalline metal, the material is made up of many tiny crystalline grains, each with the same crystal structure, but oriented in different directions. At the boundaries between grains, the regular lattice pattern is disrupted. Electrons traveling from one grain into another encounter this disruption and scatter. In very thin wires or nanoscale structures, surface scattering becomes important too. Electrons reaching the surface of the wire bounce off it and lose their directed momentum. All of these scattering mechanisms, phonons, impurities, defects, boundaries, and surfaces contribute to electrical resistance. Resistance is not a mysterious friction that slows electrons down. It is a quantum scattering process. The electron wave functions interact with imperfections in the lattice potential, changing direction, losing coherence, and dissipating the organized energy of the current as heat. The energy that the electromagnetic field pushes into the wire, driving the current, is scattered by these interactions and converted into thermal energy, random vibrations of the lattice. This is why wires get warm when current flows through them. The electromagnetic field pours energy into the electrons. The electrons scatter off lattice imperfections and transfer that energy to the lattice as phonons. The lattice vibrates more and the wire heats up. Resistance, heating, and energy dissipation are all aspects of the same quantum scattering process. The relationship between these scattering mechanisms also explains a beautiful regularity in the behavior of metals. At very low temperatures, phonon scattering becomes negligible because the lattice barely vibrates. The remaining resistance comes from impurities and defects, which do not change with temperature. This leftover resistance at very low temperatures is called the residual resistance. It tells you how pure and how perfect the crystal is. Above a certain temperature, phonon scattering dominates. The resistance increases with temperature in a predictable linear way. This behavior is universal across metals. Copper, gold, silver, aluminum all show the same pattern. It is a direct consequence of the quantum mechanics of electron scattering in a crystalline lattice. The concept of a sea of electrons in a metal, often called the Fermi sea, named after the Italian physicist Enrico Fermi, brings all of these ideas together. Imagine all the energy states available to electrons in a metal's conduction band. Start filling them from the bottom, respecting the Pauli exclusion principle, 2 electrons per state, 1 spin up and 1 spin down. At absolute zero, you fill states until you run out of electrons. The energy of the highest occupied state is called the Fermi energy. Below this energy, every state is filled. Above it, every state is empty. The boundary between filled and empty states is sharp at absolute zero. The sea of filled states below this boundary is the Fermi sea. At non-zero temperatures, the boundary becomes slightly blurred. Some electrons near the top of the Fermi sea gain enough thermal energy to jump into states just above the boundary. But only a tiny fraction of the total electrons are affected. Most electrons, those deep in the Fermi sea, far below the Fermi energy, are completely unaffected by temperature. They are buried so deeply that the thermal energy available at room temperature is negligible compared to the energy they would need to jump to an empty state. Only the electrons near the very top of the Fermi sea, within a thin energy shell around the Fermi energy, participate in electrical conduction and respond to applied fields. This explains something that puzzled physicists for decades. If metals have enormous numbers of free electrons, roughly 1 per atom, you would expect them to contribute significantly to the metal's heat capacity. Each electron should absorb thermal energy and contribute to the total energy stored in the material. But experiments showed that the electronic contribution to heat capacity in metals is tiny, far smaller than what a classical calculation predicted. The Fermi sea and the Pauli exclusion principle explain why. Most electrons cannot absorb small amounts of thermal energy because all the states near them are already full. Only the small number of electrons near the Fermi surface have empty states nearby to jump into. So only a thin shell of electrons near the top of the sea absorbs thermal energy. The rest are frozen out, locked in place by the exclusion principle, unable to respond to thermal fluctuations. This was one of the early triumphs of quantum mechanics applied to solid-state physics. And now, let us consider what happens when resistance vanishes entirely. Because there is a phenomenon in nature that is perhaps the most dramatic demonstration of quantum mechanics operating at a macroscopic scale, visible and measurable in the laboratory, not just in abstract equations. This phenomenon is superconductivity. In 1911, a Dutch physicist named Heineke Kamerlingh-Onnes was studying the electrical resistance of mercury at extremely low temperatures. He had recently succeeded in liquefying helium, reaching temperatures below 4 Kelvin, just 4 degrees above absolute zero. When he cooled a sample of mercury below about 4.2 Kelvin, the resistance did not just decrease gradually as expected, it dropped to zero. Not approximately zero, not very close to zero, exactly zero. Measurably, verifiably, completely zero. A current started in a superconducting ring will flow forever, without any voltage applied, without any energy input, without any loss whatsoever. Experiments have monitored persistent currents in superconducting rings for years, with no measurable decrease. The current just keeps flowing endlessly, without resistance, without dissipation, without decay. It is perpetual motion for electric current, something that would be impossible in any classical system. How is this possible? The answer lies deep in quantum mechanics. In 1957, 3 American physicists, John Bardeen, Leon Cooper, and J. Robert Schrieffer, published a theory explaining superconductivity that earned them the Nobel Prize in Physics. Their theory, known as BCS theory, showed that at sufficiently low temperatures, something extraordinary happens to the conduction electrons in certain materials. Under normal conditions, electrons repel each other because they are all negatively charged. But in a superconductor, below its critical temperature, electrons form pairs. These are called Cooper pairs, named after Leon Cooper. The pairing mechanism is subtle and counterintuitive. An electron moving through the crystal lattice attracts the positively charged atomic nuclei around it ever so slightly. The nuclei shift inward toward the electron by a tiny amount. This creates a region of slightly higher positive charge density, which in turn attracts a second electron. The 2 electrons are not right next to each other. They can be separated by hundreds of nanometers, hundreds of atomic spacings apart, but they are quantum mechanically correlated. They form a bound pair through the intermediary of the lattice vibrations, through the exchange of virtual phonons. These Cooper pairs have a remarkable property. While individual electrons are fermions, particles that obey the Pauli exclusion principle and cannot share the same quantum state, a Cooper pair behaves as a boson. Bosons are not subject to the exclusion principle. Many bosons can occupy exactly the same quantum states simultaneously. When the temperature drops below the critical temperature, vast numbers of Cooper pairs condense into a single shared quantum state. All of them occupy the same ground state simultaneously. This is called a condensate, and it is a macroscopic quantum phenomenon. A vast number of particles, all behaving as one single quantum entity, spread across the entire material. This condensate is why resistance vanishes. In a normal metal, individual electrons scatter off phonons, impurities, and defects, losing energy and creating resistance. But a Cooper pair in the condensate cannot scatter in the same way. Scattering would require breaking the pair, which costs energy equal to the pairing energy, called the superconducting energy gap. At temperatures below the critical temperature, there is not enough thermal energy available to break the pairs, so they glide through the lattice without scattering, without losing energy, without resistance. The condensate moves as a single coherent quantum object, immune to the lattice imperfections that would scatter individual electrons. For 75 years after Kamerlingh-Onnes's discovery, superconductivity seemed confined to the coldest reaches of temperature. The materials that exhibited it, metals and simple alloys, required cooling to within a few degrees of absolute zero. This made superconductivity a laboratory curiosity rather than a practical technology. Liquid helium, the only coolant cold enough, is expensive, scarce, and difficult to handle. The dream of resistance-free electrical transmission seemed permanently locked behind a wall of impractical refrigeration. Then, in 1986, something unexpected happened. Two physicists working at an IBM research laboratory in Zurich, Georg Bednorz and K. Alex Mueller, discovered superconductivity in a ceramic material, a compound of barium, lanthanum, copper, and oxygen. This was shocking for two reasons. First, ceramics are normally insulators. They do not conduct electricity at all under normal conditions, let alone conduct it without resistance. Second, and far more importantly, this ceramic superconducted at a temperature of about 35 Kelvin. That may still sound cold, and it is, but it was far warmer than any previously known superconductor. Within a year, other researchers found related ceramic compounds that superconducted at even higher temperatures. One compound, a mixture of yttrium, barium, copper, and oxygen, known by the shorthand YbCO, superconducted at about 93 Kelvin. This crossed a critical practical threshold because 93 Kelvin is above the boiling point of liquid nitrogen, which is 77 Kelvin. Liquid nitrogen is cheap, abundant, and far easier to work with than liquid helium. Suddenly, superconductivity became accessible. But here is the deeper puzzle. BCS theory explains conventional superconductors beautifully. The phonon-mediated Cooper pairing mechanism works perfectly for metals and simple alloys, but it does not fully explain why these ceramic materials superconduct. The pairing mechanism in high-temperature superconductors remains one of the biggest unsolved mysteries in condensed matter physics. Physicists know that electrons in these materials form pairs, and they know that the pairs condense into a quantum state that carries current without resistance. But the glue holding the pairs together does not appear to be ordinary phonons. Something else is binding the electrons. Something related to the complex magnetic behavior of these layered copper oxide structures. But nobody has definitively identified what it is. Decades of intense research by thousands of physicists worldwide have narrowed the possibilities, but have not produced a complete theory. The answer, when it comes, will likely reveal something fundamentally new about how quantum mechanics operates in complex materials. The quest continues. Physicists keep searching for materials that superconduct at ever higher temperatures, hoping eventually to find or engineer a material that superconducts at room temperature and ordinary pressures. Such a discovery would transform civilization. Power grids that transmit electricity with zero loss, magnetically levitating trains that float without friction, computers that generate almost no waste heat. The practical implications would be enormous. Whether room temperature superconductivity is achievable remains an open question. Nature may not permit it, or it may be hiding the answer in a material we simply have not examined yet. Superconductivity, in both its conventional and high-temperature forms, demonstrates something profound about the nature of electricity. It shows that electrical resistance is not an inevitable consequence of current flowing through matter. Resistance arises from specific quantum scattering processes. And if those processes are suppressed, as they are in a superconductor, current flows without any resistance at all. Resistance is not built into the nature of electricity itself. It is an emergent property arising from how electrons interact with the imperfect lattice of a real material. Remove the scattering and you remove the resistance. Superconductivity also illustrates how quantum mechanics operates at scales you can see and touch. Most quantum effects are hidden at the atomic level, invisible without specialized instruments. But a superconducting ring carrying a persistent current is a macroscopic object, something you can hold in your hand, exhibiting a quantum effect that you can directly measure. The entire ring is in a single quantum state. The current flowing through it is a quantum phenomenon, governed by a wave function that extends across the entire macroscopic object. This is quantum mechanics made visible, tangible, and directly observable. The quantum picture of electrons inside solids, with their energy bands and gaps, their exclusion principle-driven filling of states, their Fermi seas, and scattering mechanisms, gives us a complete understanding of why different materials behave so differently when subjected to electromagnetic fields. Metals conduct because their electrons have room to move within partially filled bands. Insulators block current because their electrons are trapped in completely filled bands, separated from empty bands by large energy gaps. Semiconductors sit in between with small gaps that can be bridged by thermal energy or doping. And superconductors, under the right conditions, bypass scattering entirely, allowing current to flow without any resistance at all. This is a far richer picture than the simple classical image of electrons bouncing around inside a wire like balls in a pinball machine. The electrons in a solid are quantum objects. They are described by wave functions that extend across the entire material. Their energies are organized into bands determined by the crystal structure. Their distribution among those bands is governed by the Pauli exclusion principle. Their interactions with lattice vibrations and imperfections create resistance, and under special quantum conditions, they can pair up and flow without any resistance whatsoever. All of these phenomena, conduction, insulation, semiconduction, and superconductivity, arise from the interplay between quantum mechanics and the electromagnetic field. The electromagnetic field provides the force that drives electrons through materials. Quantum mechanics determines how those electrons are organized, which states they can occupy, and how they respond to that force. Electricity is not simply the motion of particles through a wire. It is a quantum process, governed by the wave nature of electrons and the structure of allowed quantum states inside solid matter. But even this quantum mechanical picture of electrons inside solids, beautiful and powerful as it is not the final word. Because we have been treating the electromagnetic field itself as a classical entity, a smooth, continuous field described by Maxwell's equations, we have been treating photons, the quanta of the electromagnetic field, as something that only matters when discussing light and radiation, not when discussing circuits and currents. But at the deepest level of physics, the electromagnetic field is itself a quantum field. It is quantized, just as matter is quantized. And the interactions between charged particles and this quantized field are described by the most precise and successful theory in all of science, a theory that explains at the most fundamental level what electricity truly is. That theory is quantum electrodynamics, and it is where we finally arrive at the deepest answer to the question we started with. We have now traveled from amber rubbed with fur to the quantum mechanics of electrons inside crystals. We have seen that electricity is not a substance flowing through a pipe, that the energy travels through the electromagnetic field surrounding the wire, and that the behavior of electrons inside matter is governed by quantum mechanical rules involving wave functions, energy bands, and the Pauli exclusion principle. Each layer of understanding has been deeper and more surprising than the last. But there is one more layer, the deepest layer, and it is here, at the bottom of everything, that we finally reach the most complete answer physics can currently give to the question of what electricity actually is. That answer lives inside a theory called quantum electrodynamics. Physicists usually abbreviate it as QED, and it is, by any measure, the most precise, most thoroughly tested, and most successful scientific theory in the history of human civilization. To understand what QED tells us about electricity, we need to begin with a question that might seem strange at first. What is the electromagnetic field, really? We have been talking about it as though it is a smooth, continuous thing filling space, described perfectly by Maxwell's equations. And for most practical purposes, that description works beautifully. Maxwell's equations describe circuits, radio waves, light, generators, and power grids with extraordinary accuracy. But at the deepest level, Maxwell's description is incomplete. Just as matter turned out to be not smooth and continuous, but made of discrete atoms, and just as energy turned out to be not infinitely divisible, but quantized into discrete packets, the electromagnetic field itself turns out to be quantized. The first hint of this came in 1900, when Max Planck discovered that the energy of electromagnetic radiation comes in discrete packets. He called these packets quanta, and each quantum's energy is proportional to its frequency. A few years later, Albert Einstein took this idea further. In 1905, the same year he published his theory of special relativity, Einstein proposed that light itself is made of discrete particles, which we now call photons. Each photon carries a specific amount of energy, determined by its frequency. Higher frequency light, bluer light, ultraviolet, gamma rays, consists of photons with more energy. Lower frequency light, redder light, infrared, radio waves, consists of photons with less energy. This was revolutionary. For over a century, experiments had shown that light behaves as a wave. It diffracts, it interferes, it polarizes. Maxwell's equations describe it as a wave. But Einstein showed that light also behaves as a particle. It comes in discrete, indivisible chunks. Each chunk is a photon. This dual nature of light, sometimes behaving as a wave, sometimes as a particle, was one of the early mysteries of quantum physics, and took decades to fully resolve. The resolution came through quantum field theory, the mathematical framework developed through the 1920s, 30s, and 40s by some of the greatest minds in physics. In quantum field theory, the fundamental entities are not particles and not waves, but fields. Every type of particle corresponds to a field that fills all of space. The electromagnetic field gives rise to photons. The electron field gives rise to electrons. There are fields for quarks, fields for neutrinos, fields for every fundamental particle known to exist. These fields are always present, everywhere, at every point in space. What we call a particle is actually a quantized excitation of the corresponding field. A photon is a quantum of excitation of the electromagnetic field. An electron is a quantum of excitation of the electron field. The field is the fundamental thing. The particles are what you get when you disturb the field in specific ways. Think of a calm lake. The water fills the entire basin. Now drop a pebble in. Ripples spread outward, carrying energy across the surface. But those ripples are not separate from the water. They are disturbances in the water. The water is the fundamental thing. The ripples are what happen when you disturb it. In a very rough sense, quantum fields are like the water, and particles are like the ripples. The electromagnetic field fills all of space, always. When this field is excited in the right way, a photon appears. The photon is not something separate from the field. It is a disturbance in the field, a quantized packet of the field's energy propagating through space. Quantum electrodynamics is the quantum field theory that describes the electromagnetic field and its interaction with charged particles, primarily electrons. It was developed in the late 1940s by three physicists working independently. Richard Feynman in the United States, Julian Schwinger also in the United States, and Shinichiro Tomonaga in Japan. All three arrived at the same theory through different mathematical approaches. Their work was later shown to be equivalent by Freeman Dyson, who demonstrated that the three formulations, despite looking very different on paper, were all describing the same underlying physics. Feynman, Schwinger, and Tomonaga shared the Nobel Prize in Physics in 1965 for this achievement. QED describes how electrons and photons interact. At the most fundamental level, there is only one basic interaction in the entire theory. An electron emits or absorbs a photon. That is it. Every electromagnetic phenomenon in the universe, every spark, every bolt of lightning, every beam of light, every radio broadcast, every chemical bond, every electrical circuit, ultimately reduces to electrons emitting and absorbing photons. This single interaction, repeated in countless variations and combinations, generates the entire richness of electromagnetic phenomena. Feynman developed an extraordinarily useful visual tool for representing these interactions, now called Feynman diagrams. In a Feynman diagram, straight lines represent electrons moving through space and time. Wavy lines represent photons. At every point where a straight line meets a wavy line, an electron has emitted or absorbed a photon. These diagrams are not just illustrations. They correspond precisely to mathematical expressions. Each diagram represents a specific contribution to the probability of a given process occurring. To calculate the probability of any electromagnetic process, you draw every possible Feynman diagram for that process, translate each diagram into a mathematical expression, and add them all up. The simplest processes involve just a few diagrams. The interaction between two electrons, for example, starts with the simplest possible diagram. One electron emits a photon. That photon travels across to the other electron and is absorbed. This exchange of a photon between two electrons is what creates the electromagnetic force between them. Two electrons repel each other because they exchange photons back and forth. The photon carries momentum from one electron to the other, deflecting their paths, pushing them apart. This is the quantum mechanical explanation for the force between charges that Coulomb described mathematically in the 1780s. The force is not transmitted by some mysterious action at a distance. It is carried by photons exchanged between the charged particles. But these are not ordinary photons. You cannot detect them with your eyes or with a camera. They are what physicists call virtual photons. A virtual photon is a quantum of the electromagnetic field that mediates force between charges, but is never directly observed as a free particle. It exists only during the brief interaction between two charged particles. It does not travel independently through space the way a real photon from a light bulb or a star does. It cannot be captured by a detector. It is, in a sense, the field in the act of transmitting force. This distinction between real photons and virtual photons is crucial for understanding what electricity is and what it is not. Real photons are the quanta of electromagnetic radiation. They are what light is made of. When you see a light bulb glowing, the photons entering your eyes are real photons. When a radio tower broadcasts a signal, the electromagnetic waves carry real photons. Real photons travel through space at the speed of light, carry energy and momentum, and can be detected by instruments. Virtual photons are different. They mediate force. They are the mechanism by which charged particles interact with each other. When two electrons repel each other, the interaction is carried by virtual photons exchanged between them. When a proton in a nucleus attracts an electron in an atom, holding the atom together, that attraction is mediated by virtual photons. When conduction electrons in a copper wire respond to an electric field, it is through the exchange of virtual photons with the sources of that field. Now, here is where a common misunderstanding arises, and it is important to address it directly. Sometimes people hear that the electromagnetic field is quantized, that its quanta are photons, and they jump to the conclusion that electricity is made of photons. This is not correct. Electricity is not made of photons in any simple or straightforward sense. Photons are the quanta of the electromagnetic field, yes, but electricity is not the field alone. Electricity is the entire process, the interplay between charged particles and the electromagnetic field. It involves electrons as charge carriers. It involves the electromagnetic field as the medium of interaction and the carrier of energy. It involves virtual photons, mediating forces, and real photons, carrying electromagnetic radiation. Saying electricity is made of photons is like saying a symphony is made of air molecules. The air molecules carry the sound waves, but the symphony is the organized pattern of vibrations, the notes, the rhythms, the harmonies, the entire coordinated process. The air is essential, but it is not the symphony. Similarly, photons are essential to electromagnetic interactions, but they are not electricity. Electricity is the quantum process in which charged particles interact through the electromagnetic field. The photons are part of that process, but so are the electrons, the quantum states, the band structures, the fields, and the collective behavior of all these elements together. QED achieves something remarkable. It gives us the ability to calculate electromagnetic processes with a precision that borders on the absurd. The theory's predictions have been tested against experiments to a degree unmatched by any other theory in science. The most famous example involves the magnetic moment of the electron. Every electron behaves like a tiny magnet, and the strength of this magnetism can be expressed as a number, called the G-factor. Basic quantum mechanics on its own predicts the G-factor should be exactly 2. But QED predicts a tiny but important correction to this value, arising from the interaction of the electron with virtual photons that it continuously emits and reabsorbs. The electron is never truly alone. It is always surrounded by a cloud of virtual photons flickering in and out of existence, affecting its properties. When you calculate this correction using QED, working through increasingly complex Feynman diagrams involving more and more virtual photon exchanges, you get a prediction for the electron's G-factor that agrees with the experimentally measured value to better than 10 parts in a trillion. Let me say that differently to make the precision clear. If you measured the distance from New York to Los Angeles to the same relative precision, your measurement would be accurate to within the width of a human hair. QED's prediction of the electron's magnetic moment is the most precise prediction in all of science, matched by the most precise measurement in all of science. Theory and experiment agree to more than 10 decimal places. Nothing else in human knowledge comes close to this level of precision. This extraordinary accuracy tells us something deep. QED is not just a useful approximation. It is capturing something true about the fundamental nature of reality. The quantum field description of electromagnetic interactions, with its virtual photon exchanges, its Feynman diagrams, its calculation rules, is describing something real about how nature works at its most fundamental level. QED also explains the vacuum in a completely new way. In classical physics, a vacuum is simply empty space, nothing there. But in QED, the vacuum is alive with activity. Quantum fields fill all of space, even in the perfect vacuum, and these fields are subject to the Heisenberg uncertainty principle. They cannot sit perfectly still, they must fluctuate. The electromagnetic field in a vacuum constantly fluctuates, briefly creating virtual photons that appear and disappear. The electron field in a vacuum constantly fluctuates, briefly creating virtual electron-positron pairs that flash into existence and annihilate each other almost immediately. These vacuum fluctuations are not theoretical speculation. They have measurable physical effects. The Lamb shift, discovered by Willis Lamb in 1947, is a tiny difference in the energy levels of hydrogen that cannot be explained by basic quantum mechanics. QED explains it perfectly as the result of vacuum fluctuations affecting the electron inside the hydrogen atom. The virtual photons popping in and out of the vacuum slightly alter the electric field experienced by the electron, shifting its energy levels by a tiny but measurable amount. The Casimir effect, predicted by Hendrik Casimir in 1948 and experimentally confirmed decades later, is even more dramatic. Place two uncharged metal plates very close together in a vacuum. According to QED, the vacuum fluctuations between the plates are restricted because only certain wavelengths of virtual photons can fit in the gap. Outside the plates, all wavelengths are possible. This imbalance creates a measurable force pushing the plates together. The vacuum itself, the supposedly empty space between the plates, exerts a physical force. This force has been measured. It is real. Empty space is not empty. It is a seething quantum landscape of fluctuating fields, and those fluctuations have measurable consequences. Now, let us bring everything together and synthesize the full answer to the question we began with. What is electricity made of according to quantum physics? Electricity is not a substance. It is not a fluid that flows through wires. It is not a stream of tiny sparks. It is not simply electrons. It is not simply photons. It is not simply the electromagnetic field. It is all of these things working together as a unified quantum process. At the most fundamental level, electricity is the behavior of electric charge interacting through the quantized electromagnetic field. In ordinary circuits, the charge carriers are electrons, quantum particles described by wave functions, organized into energy bands by the crystal structure of the material, governed by the Pauli exclusion principle. These electrons respond to electromagnetic fields by shifting among available quantum states. Their organized drift constitutes electric current, but the electrons themselves barely move. The energy is carried, not by the drifting electrons, but by the electromagnetic field surrounding the conductor. This field propagates at nearly the speed of light, delivering energy from sources to devices almost instantaneously. The electromagnetic field itself is quantized. Its quanta are photons. Virtual photons mediate the forces between charges, transmitting the electromagnetic interaction from one particle to another. Real photons carry electromagnetic energy as radiation. The interaction between electrons and photons, the single fundamental vertex of QED, where an electron emits or absorbs a photon, is the building block from which every electromagnetic phenomenon is constructed. The strength of this interaction is governed by a number called the fine structure constant, often denoted by the Greek letter alpha. Its value is approximately 1/137. This single-dimensionless number determines how strongly electrons and photons interact. It sets the scale for atomic structure, for chemical bonding, for the properties of materials, for the behavior of light. Everything we call electricity ultimately traces back to the strength of this coupling between charge and field, and nobody knows why it has this value. This is one of the deepest unsolved mysteries in all of physics. The fine structure constant is not predicted by any known theory. It is not derived from any deeper principle. It is simply measured, and the measured value is approximately 1/137. Richard Feynman, one of the creators of QED, called it one of the greatest mysteries of physics. He wrote that all good theoretical physicists put this number up on their wall and worry about it. It is a pure number, with no units, no dimensions, just a ratio, and it governs everything electromagnetic. If alpha were significantly larger, electromagnetic forces would be stronger. Electrons would bind more tightly to nuclei, atoms would be smaller and harder. Chemistry would change dramatically. The energy levels in atoms would shift, and the chemical bonds that hold molecules together, including the molecules of life, would behave differently. If alpha were significantly smaller, electromagnetic forces would be weaker, atoms would be larger and more loosely bound. Complex chemistry might not occur at all. Stars might not produce the heavy elements needed for planets and life. The universe would be a profoundly different place. We exist in a universe where alpha has exactly the value needed for atoms to form, for chemistry to work, for materials to conduct or insulate, for light to interact with matter in the precise way that enables vision, photosynthesis, and the entire electromagnetic foundation of biology. Whether this value is a cosmic accident, a consequence of some deeper theory we have not yet discovered, or a selection effect in a vast multiverse of different possible physics, remains one of the great open questions. The fine structure constant sits at the heart of electricity, governing every interaction between every charged particle and every photon in the universe. And we do not know why it is what it is. So when you flip a light switch, here is what actually happens. Described at the deepest level physics can currently reach. Closing the switch completes a conducting pathway. An electromagnetic field establishes itself throughout the circuit, at close to the speed of light. This field, a quantum field whose excitations are photons, carries energy from the power source through the space surrounding the wires. Inside the wires, electrons in partially filled quantum energy bands respond to the field by shifting among available states, creating a net drift of charge. This drift is electric current. The electromagnetic field surrounding the wire funnels energy toward the light bulb. Inside the bulb's filament, electrons scatter off lattice vibrations and imperfections, converting the field's energy into thermal motion, heating the filament until it glows. The glowing filament emits real photons, quanta of the electromagnetic field, which travel at the speed of light to your eyes. Your retinal cells absorb these photons, triggering electrochemical signals, which are themselves mediated by the electromagnetic interaction between charged particles in your neurons. You see light. Every step of this process, from the establishment of the field, to the drift of electrons, to the emission of light, to the electrochemistry of vision, is governed by QED. Every step involves the interaction of charged particles with the quantized electromagnetic field. Every step reduces at the deepest level to electrons emitting and absorbing photons. And yet, none of these steps involves a substance called electricity flowing like water through a pipe. There is no electrical fluid. There never was. What exists is electric charge, a fundamental property of matter. What exists is the electromagnetic field, a quantum field, filling all of space. What exists is the interaction between them, governed by the most precise theory humans have ever constructed. Electricity is the name we give to the collective behavior that emerges when charged particles and electromagnetic fields interact in organized ways. This understanding has a strange and beautiful implication. When you look at the wires running through your walls, you are looking at guides for a quantum field. When you feel the warmth of a wire carrying current, you are feeling the energy of that field being absorbed by the material through quantum scattering. When you see light from a bulb, you are seeing real photons, individual quanta of the electromagnetic field born from the thermal agitation of electrons in a hot filament. When you charge your phone, you are using an electromagnetic field to rearrange ions and electrons inside a battery through quantum electrochemical processes. Every electrical device you own, every lamp, every motor, every screen, every speaker, operates through the quantum interaction of charged particles and the electromagnetic field. We live immersed in this quantum field process. Every nerve signal in your body is an electrical event. Every beat of your heart is triggered by electrical impulses. The thoughts you are having right now as you process these words involve billions of electrochemical signals racing through your brain, each one a quantum electromagnetic process, each one involving electrons shifting among quantum states and electromagnetic fields propagating between cells. You do not merely use electricity. You are, in a very real sense, an electrical phenomenon yourself. Your consciousness, your awareness, your ability to wonder about what electricity is, all of it arises from the quantum electromagnetic interactions happening inside your nervous system at this very moment. Consider what that means. The same force that pulls a scrap of straw toward a piece of rubbed amber, the same force that Thales noticed 26 centuries ago without the faintest idea what he was looking at, is the force holding every atom in your body together. It is the force that shapes the proteins in your cells. It is the force that transmits every signal along every nerve. It is the force that makes your heart beat and your lungs breathe and your brain think. The electromagnetic interaction governed by QED, mediated by photons, carried by the quantum electromagnetic field, is the physical foundation of your existence. You are not just a user of electricity, you are a structure built by it, sustained by it, animated by it. Every flicker of thought in your mind is an electromagnetic event. Every memory you have ever formed was written by charged particles interacting through quantum fields. The universe gave us electric charge as a fundamental property of matter. It gave us the electromagnetic field as the medium through which charges interact. It gave us photons as the quanta of that field, and electrons as the quantum carriers of charge. And from these ingredients, governed by the elegant mathematics of quantum electrodynamics, emerges everything from lightning to starlight, from radio waves to the firing of neurons, from the warmth of a wire to the glow of a screen. Electricity is not a thing, it is a process, a quantum field process involving charged particles and the fields that connect them. It is one of the most fundamental processes in nature, woven into the fabric of the universe at its deepest level. And every time you flip a switch and light fills the room, you are witnessing quantum electrodynamics in action, the most precisely verified theory in human history, operating silently, invisibly, and flawlessly, right there in your living room.